Hi everyone, I'm Peng Zhanxun, a second-year PhD student from National University of Singapore. Today I'm going to give a presentation about my ICCV paper, Visual Intention Grounding for Egocentric Assistance. Before we dive into the paper, let's first talk about why understanding human intentions is important in vision language models. So let's consider such a scenario. I want to display my laptop screen on the monitor. So actually I need to provide my AI assistant with clear actionable steps. For example, first, find an adapter from the scene. Second and third. However, if my AI assistant can understand human intention, then I just tell my goal without needing detailed instructions. Then the AI assistant infer my context and then generate a step-by-step plan automatically. So, understanding human intentions actually brings us smarter AI assistants. It can help to support contextual and goal-directed interaction, respond proactively, not just reactively. It can infer next steps in a task. It can reduce unnecessary clarifications. To achieve that, visual grounding is a key enabler. So the task of visual grounding definition, it establishes the connections between linguistic expressions and their corresponding visual elements. So the input of this task can be an image plus the language description, and the output should be the bounding box of language description. Visual grounding has extensive applications, for example, visual language navigation, human-machine dialogue, and wearable AI assistants. There are two main gaps in visual grounding research. The first one is the lack of egocentric data, and the second one is the limited coverage of complex intentions. So in this paper, we propose a novel dataset for visual intention grounding, which is EgoIntention. This is our teaser figure. So for the left one, this is an illustration of conventional visual grounding. The input language query can be in an explicit way. For example, white chair. And also the image is just insert person view. However, we believe that a wearable AI assistant should also be able to identify contextually relevant objects from a first-person view, without explicit object references. Human user can directly express their need or their intention. For example, I need a little boost to reach the sink. So in such kitchen scenario, the AI assistant should be able to help us find, for example, a chair to boost the height. Our dataset EgoIntention, it sources the images from Ego 4D dataset and the associated object bounding box annotations from another dataset paper named PACO. However, we highlight our key contribution, which is the collection of multiple intention queries per object. This reflects the diverse ways objects are used in real-world scenarios. In our dataset, we designed two types of intention descriptions. The first one is context-aware intentions, and the second one is uncommon intentions. So for the first one, these sentences reflect complex object relationships and also the environmental cues. For the second type of intention sentences, they describe uncommon object uses, where users can repurpose objects based on the necessity. Here is how we define the context and uncommon intention. So we inspired by this paper, And in this the functional correspondence problem paper, it classifies object affordances as primary, secondary. So building on top of this, we can construct a primary affordance list for objects in our dataset. So you can see the table below as an example. So it is very straightforward that an intention sentence is considered uncommon if it describes a need or usage of an object that differs from its primary affordance. Here is the pipeline of our dataset collection. The first step is intention description generation. We input the ground truth object and the bounding boxes, and also, of course, the first person view image. We input all these into ChatGPT to generate some candidate sentences. Here we paste some examples for the intention description generation step. Now let's move to the experiments. Our zero-shot evaluation covers off-the-shelf model like GPT-4 or grounding Dino, and also grounding specialist multimodal large language model, for example, CockBLM, grounding, and Groma. And also we cover generalist multimodal large language model like Mini GPT version 2 and Q1VL. We test all the models on RefCoco datasets and also our own built Egointention dataset and leverage the precision at 0.5 as the metric. A straightforward method is to leverage off-the-shelf model pipelines. We can first detect candidate object bounding boxes and then do a matching between boxes and intention query. Also, we can first reason about the target object and then detect this object. And from our results, we find that performing reasoning first improves the accuracy because this can narrow down the search space before detection, which leads to more precise object localization. For grounding specialist multimodal large language models such as CogVLM grounding and GROMA, these models usually perform poorly on our Egointention dataset. This is because during training stage for these kind of grounding specialist model, um, the data they use is only explicit object query, so it cannot handle the implicit human query. However, for the generalist multimodal large language models such as Mini GPT version 2 or QNVL model, they demonstrate more reasonable grounding performance when given an intention query. This is because these kind of generalist multimodal large language models already have some reasoning ability because these models are not trained only for the grounding task. It also for reasoning task or QA task. We also fine-tuned the Mini GPT version 2 and the Q1 model with the mixed dataset, which is both RefCoco dataset and our Egointention dataset. So we find that compared with the naive SFT baseline, our ROG instruction training strategy, it can not only enhances the performance on Egointention dataset, but also leads to more accurate results on the RefCoco dataset. We studied the performance gains from two benchmarks. So to avoid performance drop on the traditional third-person view dataset RefCoco, we conduct supervised fine-tuning on mixed datasets. And we find that joint naive supervised fine-tuning on RefCoco dataset and Egointention dataset outperforms models trained on either dataset alone. There are also some interesting findings. For example, our method also leads to a significant improvement on egocentric visual grounding with explicit object queries. We also do some experiment analysis on object reasoning error. So the first type of reasoning error, we define it as misleading language, which means like the output object is in the language query, but it is actually not the intended object. It is not the object we need. The second type of error, we name it as misleading vision. Similarly, it means like the reasoning object is from the image. It appears in the image, but it is still not the intended object, not the object we want. Then the third type of error is hallucination, which means like the reasoning object is neither in the language query nor in the image. We find the reason to ground supervised fine-tuning Mini GPT version 2 shows lower error rates in all three categories. Then let's discuss the impact of our uncommon intention annotations. which is a subjective and underexplored topic. Existing RIO real dataset, they offer 4,000 test-only cases, but without any training data. As for the experiment results, we observed that removing our uncommon data drops the precision at 0.5 on EgoIntention, and adding the uncommon intention data, then it can boost the zero-shot real RIO performance for both naive and ROG supervised fine-tuning. Here are the visualization of context-aware intention sample. Then these are the uncommon intention samples. Now let's conclude the paper. Firstly, we construct the EgoIntention dataset for visual intention grounding. So our dataset is the first egocentric visual grounding dataset with multiple intention queries. Second, we benchmark and review that existing multimodal large language models struggle with intention reasoning and egocentric visual grounding. Actually, these models misinterpret explicitly mentioned objects as targets, or hallucinate objects not present in the scene. Third, we propose reason to ground instruction training method, which is a model-agnostic training approach to enhance the existing multimodal large language models for egocentric intention grounding. And in the meantime, it can retain the performance for the traditional third-person view visual grounding. Okay, that's all. Thank you for listening.